Welcome back, guys. This is 11.5. We're looking at area and lengths in polar coordinates. Let's start with looking at area. So let's say, suppose we have a polar graph, with just a segment like this, right? And we want to find the area under the curve, right? So most of the time, let's say there's a loop right here. We want to find the area of the loop. Now, since this is in polar coordinates, we are looking at r and theta, right? Each of the point has the coordinate r and theta. Okay, so what we're going to look at is the same idea of a definite integral, right? Which we want to split the area under the curve into little rectangles. But here, instead of looking at rectangles, we're going to use this little triangle to calculate our area, right? So for each of the curve, we can build a triangle like that, and then we can make it as small as possible, as small as we want, to get the most accurate estimation, right? So that's the basic idea. Now, next, let's just look at one triangle and let's try to understand what we're looking at here. All right. So we have the point P and our theta. And as we change our theta, right, this is what happens, right? Well, we have a little change in theta, which is d theta, right? Change in theta, which affects the angle that it forms with the x-axis, right? And our radius is the same, right? Radius is the same. So only theta changes, but radius is actually going to change a little bit, but it's not going to be a big deal, right? So the area is going to be base times height. In this case, the height is r, right? And the base can be found using the value of d theta, right? So we're actually just assuming that this is our d theta, which is the formula for the arc length, right? And then let's say this is r d theta multiplied by r and multiplied by 1/2. That will give you the area of this triangle, right? Triangle is base 1/2 base times height. So that's the basic idea. And if we add everything together, right, all the little triangles together, we will receive the formula. Now the area in a fan-shaped region between the origin and the curve, right? So in most cases, it's going to be our polar graphs. It's going to be the integral from alpha to beta 1/2 r squared d theta, right? Remember earlier, 1/2 r squared d theta, that's our area for one little triangle, one piece of the triangle, right? And we wanted to integrate it from alpha to beta, where alpha and beta are our theta, right? Just like the bounds of limitation when we're looking at just a simple graph, right, from A to B, right, from A to B, right. In this case, we're looking at angles, right, so that's we're using alpha and beta. Right. So yeah, that's the formula, and this is the integral of the area differential, which is what we're looking at here, up here, right. So we're integrate all the little triangles, all the thetas from alpha to beta. All right, so let's take a look at one example. All right, here we go. Example 1, find the area of the region in the xy plane enclosed by the cardioid r equals to 2 times 1 plus cosine. All right, so let's go ahead and do that. We have r, right, and then we have the formula up here. Area is equal to alpha to beta 1/2 r squared d theta. Right. So notice that when we look at this graph, one complete cycle is actually going from 0 to 2 pi, right? As it notes here, it goes back to this point, 4, 0, right? And then comes back again when you hit 2 pi, right? So in this case, our theta goes from 0 to 2 pi, and that's where we're going to take our integration until. Right, so here we go. That's equal to integral 0 to 2 pi 1/2 r square. R is 2 times 1 plus cosine theta square, right? D theta. All right, let's expand this a little bit. 0 to 2 pi. Right, so 2 squared, that's 4 times 1/2, that's a 2. And then we need to expand 1 plus cosine theta square as well. Right, let's do that next. Right, let's see what we have. This is going to be 0 to 2 pi, 2 times 1 plus 2 cosine theta plus cosine square. Right, and then let's multiply the 2 into the parentheses. Right, we have 2 plus 4 cosine theta plus 2 times. Now, cosine square, I'm actually going to use the double angle formula. That is cosine square theta is equal to 1 plus cosine 2 theta over 2. Right? Because we cannot integrate cosine square, we need to use a double angle for cosine to integrate. All right, so 1 plus cosine 2 theta over 2. Right, and then d theta. D theta. Let me put everything in parentheses here. All right, so we can now integrate each one of them. All right, so 2 will be 2 theta, 4 cosine will be 4 sine, right? And this whole thing in our last term, this is just 1 plus cosine 2 theta, right? So integrate that, we get plus theta plus sine 2 theta over 2, right? By the chain rule. All right. And we're evaluating this from 0 to 2 pi. Actually, I'm going to combine the thetas together. So we have 3 theta plus 4 sine theta plus sine 2 theta over 2, evaluating from 0 to 2 pi. All right, so let's see what we have. That's 6 pi, sine of 2 pi is 0, sine of 4 pi is 0, minus 0 plus 0 plus 0, right? So we get 6 pi, right? And that will be the area of the cardioid, which is this, I want to say peach look like thing, or maybe an apple, right? So a lot of the graphs for polar equation actually looks like some kind of fruit or flower, right? Which is very interesting. All right, and that's basically how you use the formula. I think it's very straightforward. Just some techniques of simplifying tricks, integrating tricks are very important here. All right, let's look at another example. Just like Cartesian functions, we can also look at the area between two curves, right? For example, if we have two polar equations, R1 and R2, and we want to look at the area that's bounded by these two functions, right? So take the same thing, we take the area under R2, subtract the area under R1, and then to simplify it, we can just do 1/2 of R2 squared minus R1 squared. Right, so it's basically the same thing with regular Cartesian functions. It's just that to find the integral under the polar curve, we need this extra 1/2 and then the square on the function, right? But that is not a big problem because we can just factor out the 1/2 and then just do R2 squared minus R1 squared. All right, and let's take a look at example 2. Find the area of the region that lies inside the circle R1, right? So that's a circle with radius 1, and outside the cardioid R equal to 1 minus cosine. All right, so first we want to know where these two functions, these two graphs intersect each other, right? Right. Find intersections. Right? That way we will be able to know where to take our limits of integration. Right? So let's say R1 is the circle and R2 is the cardioid. Let R1 equal to R2. Right? So 1 is equal to 1 minus cosine theta, and we get a cosine is equal to 0. Cosine is 0 from negative pi over 2. At negative pi over 2 pi over 2, negative pi over 2, and pi over 2. Okay, or 3 pi over 2, depends on what you're feeling, right? But the question is, do we take from negative pi over 2 to pi over 2, or from pi over 2 to 3 pi over 2, right? Because negative pi over 2 and 3 pi over 2, they both make cosine 0. But we want to make sure which one is the segment that we want, right? From negative pi over 2 to pi over 2, or from 3 pi over from pi over 2 to 3 pi over 2. Okay. Now the easiest way to do that is by graphing, right? You can use Desmos, or on your graphing calculator, you can graph these two functions out, right? So fortunately, we do have a picture that's very nice. All right, so we can see that inside the circle and outside of the cardioid, actually they use R1 to represent the cardioid. Let's do that. Okay, let me just fix that. R2 is the R1 is the cardioid, and R2 is the unit circle. All right, outside of the peach, outside of the cardioid, and then inside the unit circle. All right, so we can see that it's actually on the right hand side, right, which goes from negative pi over 2 to pi over 2. Right, so we are correct, right? If we took pi over 2 to 3 pi over 2, then we will get a different different value, right? Different area for this question, for this definite integral. Right, so you want to make sure to be very careful with your limits of integration. All right, now that we know the bounds from negative pi over 2 to pi over 2, we can apply the formula. Okay, okay, let's take a look at the area formula. Integral from alpha to beta, 1/2 R2 square minus R1 square d theta, right? The one on the outside, the unit circle, subtracting the one on the inside, which is the cardioid R1. All right, and the bounds are from negative pi over 2 to pi over 2. All right. Now notice that R2 square and R1 square is going to make this whole thing an even function, right? Since it's an even function, what we can do is, since the bounds are symmetric to each other, we can actually just take half of it from 0 to 2 pi and then double whatever the value is. All right, so we can rewrite that as 2 times 0 to pi over 2, 1/2, and then R2, which is just the unit circle 1 square, minus R1, the cardioid, 1 minus cosine theta square d theta. Okay, all right, so that's one thing can make our lives a little easier, right? Since we know that it's an even function, we can rewrite the bounds to go from 0 to pi over 2 instead of from negative pi over 2 to pi over 2, because they're symmetric, right? If you look at the area, right, they're symmetric, and we can just calculate the top side and then multiply by 2. All right, let's go ahead and evaluate this. So 2 times 1/2, so that's just 1, 0, pi over 2, and then we have 1 minus 2 cosine theta plus cosine square. All right, so we see the cosine square again in the integral. We know what to do, right? All right, so let's simplify this a little bit. All right, 1 minus 1, that's gone. It will be 2 cosine theta, and then minus cosine theta. So I'm going to rewrite cosine theta as 1 plus cosine 2 theta over 2. Right, and d theta. Okay, now we can integrate everything. All right, 2 cosine theta, that's just 2 sine theta, minus 1/2, right? So minus theta over 2, and then minus cosine 2 theta over 2, that's going to be minus sine 2 theta, and divide by another 2, so 4. Okay, and evaluate everything from 0 to pi over 2. All right, here we go. Sine of pi over 2 is 1, so that's a 2 minus pi over 4. Sine of 2 times pi over 2 sine of pi, that's 0. Right? Minus 2 sine 0, 0 minus 0 minus 0. All right, so it's 2 minus pi over 4. And that's our final answer. All right, so the actual working out the problem is actually not too bad. I think the more interesting part of this question is finding the intersection, right? Because we can represent a point in many different ways in the polar coordinates, and that means we have to be very careful when we are determining the point where the polar graphs intersect. When we're back in Cartesian coordinates, right, working with f of x, y equal to f of x, we can always find points where two curves cross by solving their equations simultaneously, right? Finding different x value. But in polar coordinates, it's a little different. Simultaneous solution may reveal some intersection points without revealing others, right? Because there are many ways to represent the same point using polar equations. So it's sometimes difficult to find all the points of intersection of two polar graphs. Now, one way to identify those intersections is very easy. It's just to graph it out, right? And then we can see clearly where the intersections are. Right? So some graphing tools will be very nice in this case, right? For example, Desmos or Wolfram Alpha, or if you prefer, you can use your graphing calculator as well. All right, let's do an example where we are required to find some intersection. Right? Example 3, find all the points where the curve r equals 2 cosine theta over 3 intersects the circle of radius radical 2, centered at the origin. Now, this is very interesting and a little tricky, kind of like a trap here. It only tells you it's a circle of radius 2, so we have to come up with the equation for a circle with radius 2. Right, the most obvious one is just take radius equal to radical 2, right? But notice that it doesn't tell us anything about the equation for that circle, so we have to think outside of the box, right? Another way to represent a circle with radius 2 is taking a negative radius, right? Because in polar coordinates we know that radius can be negative, right? So when r is equal to negative radical 2, it will also give you the same circle. So we have to consider these two possible cases, right? So let's take a look at the positive one first, right? So setting these two equations equal to each other, 2 cosine theta over 3 is equal to rad 2. That is when cosine theta over 3 is equal to radical 2 over 2. So cosine is rad 2 over 2 at negative pi over 4 and pi over 4. Okay. All right. Sorry, not theta, theta over 3, right? That means theta is negative 3 pi over 4 and pi over 4, right? That gives us the 2 points, right? R is radical 2, negative 3 pi over 4, and radical 2 pi over 4. Now let's check if they are the same point, right? They have the same radius and the angles are different, right? So actually, let me go to the bottom for this. Pi over 4 rad 2, that's about here. And, 3 pi over 4. Sorry. Oh my goodness. 3 pi over 4. Right, so that's about here, and radical 2, and negative 3 pi over 4, and rad 2 is about here. Okay, so they are the different points. That's good. Now let's check on negative 2. R is equal to negative radical 2. Right, so 2 cosine theta over 3 is equal to negative radical 2. All right, So cosine of theta over 3 is negative radical 2 over 2. And the cosine is negative radical 2 over 2 when the angle is 3 pi over 4 and 5 pi over 4. Right? That makes theta 9 pi over 4 and 15 pi over 4. Okay, so we also have the two coordinates, right, where r is negative rad 2, 9 pi over 4, and negative rad 2, 15 pi over 4. Okay, and that's graphic. Right, so 9 pi over 4, so that's one full rotation, and then pi over 4, but it's negative, so it's going to be on the other side of the 9 pi over 4, which will be right here. Right, let's call that point A. And point B is going to be 15 pi over 4, right? So that will be one rotation and then 7 pi over 4. So one rotation and then 7 pi over 4, which will be right here, right? But radius is negative, so it's going to point the other way, and that's point B. Okay, now notice that these 2 points are actually the same thing as our previous 2 points, right? So let's write them out. This top one is rad 2 and 3 pi over 4. And then the bottom one is rad 2 and negative 3 pi over 4. So rad 2, 3 pi over 4 is actually the same thing as point B down here, right? So this point is the same thing as this point, right? And this, oops, here's a different color. And this point right here, it's the same thing as point A. All right. So all in all, we can say that we know that radical 2 and 3 pi over 4 is actually the same thing as point B, which is negative rad 2, 15 pi over 4, right? And radical 2, negative 3 pi over 4, which is this point right here, is the same thing as our point A on the bottom, negative rad 2 and 9 pi over 4. Right. So from this, we can say that okay, even though we're using 2 different functions to represent the circle with radius radical 2, they both give us the same point of intersection, which are these 2 points. And then notice how we get very different polar coordinates using 2 different functions. But after all, we can have different expressions in terms of polar to represent the same point. Right? In this case, we only have 2 intersections instead of 4, even though total we found 4, but we have 2 pairs of points that represent the same thing. Okay, so here is a quick graph to show you what we're looking at. All right, so we have radical 2, 3 pi over 4, and radical 2, 5 pi over 4. Well, 5 pi over 4 or negative 3 pi over 4, right? They point to the same thing. One is positive rotation, one is negative rotation. But again, in polar, we can represent the same point with different coordinates, which can be confusing, but also can be very interesting. Okay. All right, the second part of this section, let's look at a length of a polar curve, right? Something similar to arc length. And we have the formula right here, our integral of alpha to beta, radicals square, r squared plus dr d theta squared. Right? So very straightforward formula. And let's just take a look at example 4. Find the length of the cardioid from with the equation r equal to 1 minus cosine theta. Now we actually have the graph of the cardioid earlier. Let's go back to the top, right here. Okay, so we know that the cardioid makes one full complete graph went from 0 to 2 pi, right? So 0, and then it's going to rotate, make the pitch, and then come back to the same point. Now, one thing with finding the length is that you don't want to double count, right? You don't want to go over 2 loops. For example, if you take the integral from 0 to 4 pi, then you would go over this cardioid twice, which will give you twice the length of the length, right? So we want to avoid doing that. So we have to be very careful on when do we go back to the same point, right? So we know that cardioid goes from 0 to 2 pi, right? To make one full rotation, right? So theta goes from 0 to 2 pi, right? And then we can just apply the integral, right? There we go. Length is integral from alpha to beta, square root r squared plus dr d theta square, and then d theta. All right, so let's find out what dr d theta is. R is 1 minus cosine theta. Then dr d theta will be sine. Okay. All right, let's plug everything in. 0 to 2 pi square root r squared. So that's 1 minus cosine theta quantity square plus dr d theta squared. That's just sine square. All right, d theta. All right, from this point on, it's just evaluating the integral 0 to 2 pi. But before we evaluate the integral, let's simplify the radical first. All right, so let's see what we have. We have 1 minus 2 cosine theta plus cosine square, and then plus sine square. All right, and we know that cosine square plus sine square is equal to 1. Right? So these two things equal to 1. Then we have 0 to 2 pi, 2 square root of 2 minus 2 cosine theta. All right. And now we're going to do something a little different here. I'm going to factor out the 2 first. Okay, so I have 2, and then 1 minus cosine theta. So here we're going to use a very unpopular property of trig. I'm going to write it down here. 1 minus cosine theta is actually 2 times sine square of theta over 2. Right? One of the half angle formula, and then with a little twist. Right, which is not that common, but in this case, we're going to use this. All right, so we can rewrite the whole integral as the whole radical as 2 times 2 sine square of theta over 2. All right, and then that simplifies down very nice to 2 sine theta over 2 d theta. All right. And then we can integrate it. Right? That's just will be 2 times negative cosine theta over 2, and then reverse chain rule multiplied by another 2 here. Evaluate it from 0 to 2 pi. Let's clean this up. We get negative 4 cosine of theta over 2. Going from 0 to 2 pi, which is 2 pi over 2. That's pi. Cosine pi is negative 1, so 4 minus negative 4 times cosine 0, which is 1. All right, so 4 minus negative 4, that's 8. Okay, and there you go. 8 is the final answer of the length of a cardioid. Okay. Now we used some really uncommon trig properties, but you know, there are many tables in the textbook and also online. You can find out all the trig formulas and trig properties, and so it shouldn't be that much of a problem. You just need to figure out which one to work, and from time to time the question actually gives you the hint of which one you will need, right? Okay, so that will be all for today, and yeah. So basically, we have two formulas to work with, right? The area of the region, which is 1/2 integral of 1/2 r square, and then another one is the length, which is right here, integral of radical r squared plus dr d theta square, right? So they're both very straightforward. It's just the integration part will include a lot of the trig functions and also test your understanding on polar coordinates and polar equations as well. All right. Thank you guys very much, and I'll see you next time.